Hello again. Let's do a few more problems. This is directly off the same worksheet that we went through in that excruciating detail on Thursday in class. If you missed class Thursday, then this is a must-see video for you. So it'll help you know what you're supposed to do. All right, step by step, let's do this. What distance will a car cover? Hey, sounds like we're looking for, we're looking for delta x equals. While uniformly accelerating, so there's some acceleration there, from 12 meters per second. So from that means our initial velocity is 12 meters per second to 26. So our final velocity is 26 meters per second in 14 seconds. So that's a time of 14 seconds. Before I dive into the graph, I always like to look and see if there's anything I can do real quick. Hey, if I know the two different velocities, I can get the change in velocity, which here goes from 12 to 26, so it gains 14 meters per second. Is there anything else I can do? Oh, I can get the acceleration, because remember, acceleration is the change in velocity over the change in time, and I have that. It's 14 meters per second divided by 14 seconds. So that's going to end up being 1 meter per second squared. That's an easy, convenient acceleration to deal with. All right, I think I can't do anything else with the information that I have, so let's dive into the VT graph. VT. This thing starts not with a velocity of 0, so you can't start down here. You got to start up here somewhere. That'll be your 12, your starting velocity, and it increases to 26. So let's go ahead and do that. That's your 26. And then we're done. But remember, the area under the VT graph provides the displacement. This is an odd shape, so we have to break it into two recognizable shapes. So down here, the area would be your initial velocity, which is 12 meters per second, times your time. Up here, it's a triangle, so it's 1/2, and then this is your change in velocity times time. That's your base. So because the area of this equals the displacement, we can say delta x equals v naught t plus 1/2 change in velocity times t. So do I know delta x? No, we're looking for that. Do I know v naught? Yes, I do. Do I know t? Yes, I do. Do I know change in velocity? Yes, I do. And I have the t. Do I have a dog? Yes, I do. You can hear her barking in the background. That's Carly. She's a mutt. She's a good dog. All right, so let's plug and chug. Our initial velocity is 12 meters per second times the time, which is 14 seconds, plus change in velocity times time over 2, so that's 14 meters per second times the time, which is 14 seconds, and we're going to divide that by 2. If this is ugly, I apologize because it's not really fitting on the page here, but let me rewrite all this down here a little bit more cleanly. I'll do it in a different color so we can see what's going on. Delta x equals our initial velocity times time, which is 12 meters per second times 14 seconds, plus 1/2 of our change in velocity from 12 to 26 is 14 meters per second times the time, which is 14 seconds. So if we do the math, 12 times 14 is 168 seconds go away, meters, plus 14 times 14 divided by 2 is 98, and check it out, the seconds go away, so you're left with meters again. So your total displacement is those things added up, which is 266 meters. All right, this number, who cares? What's really important is, can you list everything you have, find something that maybe pops out easily, then draw the VT graph and use the VT graph to get your equations. That's what matters, bub. All right. Okay, let's do one more. This one's tricky. There's a reason I'm choosing it. Okay, first things first, though, just like always, let's write down what the problem tells us. Cyclist is riding along at a constant velocity of 15 meters per second. he then accelerates. So this constant velocity, for the purposes that we're considering it, does it stay that? No, because it just accelerates. So we're going to say the initial velocity is 15 meters per second. That's how fast the cyclist is going before he then accelerates. He does have an acceleration of 0.5 meters per second squared over a distance, a displacement of 64 meters. And then the question is, how long did he accelerate? There's not a lot of information there, is there? So let's see what we can do with this. If I have the change of position, acceleration, and velocity, nothing pops into mind that I can do with this, so I'm going to click into the VT graph. All right, now in this case, they started with the velocity 15, and then it went up from there. So you've got this shape. So once again, you've got your initial velocity times time for the bottom part, and your 1/2 change in velocity times time up there. And we know that the area equals the displacement, so now what we can say is that delta x equals v naught t plus 1/2 change in velocity times time. There's an equation we can use. Do we know delta x? We do. Do we know the initial velocity? We do. Do we know t? No. Do we know the change in velocity? No. So I've got two variables. Maybe this isn't the best choice. Well, remember, delta v equals a times t. So if you substitute that back in, you can rewrite this equation as delta x equals v naught t plus 1/2 at squared. If you plug that thing in there, that's what happens. Let's consider this. Does this help us? Do we know delta x? Yep. Do we know v naught? V initial? Sure. Do we know t? No. Do we know a? Yes, we do. So how many variables are we left with? Just one, t. Can we use this? Yes, we can. Now it gets tough because you've got a quadratic situation. So you can rewrite this. As, if we try to, you can try to go as like, let me think. Try to solve for t is going to get tough. I think your best bet is going to subtract delta x from each side, and you end up with 0 equals v naught t plus 1/2 at squared minus delta x. Wait a minute, that looks like a quadratic, doesn't it? Let's rearrange this guy. You end up with a over 2, that's 1/2 a, t squared, plus initial velocity times time. I just moved these back and forth to get them in the quadratic formula lineup, minus delta x. So you can plug some numbers in. I want to move this over so we can see it a little better. So now we know 0 equals acceleration divided by 2 is going to be 0.25, and that's t squared, plus your initial velocity, 15 times t, minus your 64 meters. So at this point, my friends, you got to do the old quadratic equation to solve for that. Or you can remember that there are some equations that I do not expect you to memorize, but I do expect you to have in your toolbox and know when you can pull them out and use them. This may be one of those times. There is this equation, V, come on now, final, what just happened there? V final squared equals V initial squared plus 2 acceleration delta x. Do we know V final? Yes, we do. Do we know V initial? Yes, we do. Do we know the acceleration? Yes, we do. Do we know delta x? Yes, we do. And we can find V final just from going, wait, how do we know that? So you can plug your numbers in for your initial velocity, which is 15, square that, plus 2 times your acceleration, which is 0.5, times your displacement, which is 64, and then that's going to equal VF squared. So if we want to know just what VF is, we'll get rid of that and just take the square root of all this. So VF will end up being the square root of 225 plus 64, and whatever that ends up being, that's going to equal 17 meters per second. And then we know that, we can plug that back in here, Vf equals 17 meters per second. So now you've got an acceleration, you've got your final velocity, your starting velocity, and you can use these guys to solve the problem. The change in velocity equals 2 meters per second. And then we know that time equals the change in velocity divided by the acceleration. So we got 2 meters per second divided by that 0.5 meters per second squared equals 4 seconds. All right, if you have problems with this, come see me. I'm not going to ask a lot of these types of problems because it gets more mathy than it is physicsy, but do your best on these. Really follow the steps, people. If I can, I don't know if I can emphasize that enough. You have to do these things in order. And by that I mean, I'm going to hammer this out right now. This is important to me. Step 1. List what you know. Step 1A. Find other stuff from what you know, if possible. For example, if you know the acceleration and you know the time, you can find the change in velocity. Step 2, the VT graph. Super important. 3, get an equation from the VT graph. 4, plug and chug. Then 5, just check it. Make sure it makes sense. All right. I hope you're enjoying your long weekend. I hope this makes you feel better. Look, you guys, you're all smart kids. You're all capable. If you put a little bit of time into this, you can get really good at this, and let's get those quiz grades rocking. All right. See ya.